In section 1.7b, we'll be looking at absolute value inequalities. Let's start by comparing an absolute value with an equals, with a less than, and a greater than. We've already looked at the absolute value equations. Remember the geometric definition of absolute value. This is the distance between a number and the origin, or 0, on the number line. So when we say the absolute value of x equals 3, a solution would be any number that has a distance of 3 units from 0. So either 3 units to the right or 3 units to the left. That gives us two solutions to this equation, positive 3, negative 3. These are the only two numbers that are 3 units from 0. Now let's look at less than. The absolute value of x less than 3 will be true for any number that's less than 3 units from 0. So this will be true for any number that's in between negative 3 and positive 3. Anything in this interval will be less than 3 units from 0. And these have to be whole numbers like 1 and 2. They can be any fraction or irrational number in between the integers. In this case, because there's no equals, we're not including the endpoints negative 3 and positive 3. These would not be solutions. This three-part inequality is the easiest way to write this algebraically. This says that x is greater than negative 3 and x is less than positive 3. Sometimes you will see that written out separately. If you do write it out separately, it's very important that you use the word and, because it has to be both greater than negative 3 and less than positive 3. If you use the word or, you would actually have any number on the number line, because greater than negative 3 would extend all the way to the right, and less than positive 3 would extend all the way to the left. So you'd be covering every possible number. And means the intersection or the overlap of these two intervals, which is just the numbers between negative 3 and positive 3. If you're given a choice, the three-part inequality is usually easier to work with. And now let's look at greater than. Absolute value of x greater than 3 is true for any number that's more than or greater than 3 units from 0. This will be true for any number that's greater than positive 3. Any number over here will be more than 3 units from 0. Or for any number that's less than negative 3. Any number here to the left of negative 3 will also be more than 3 units from 0. This is the only way we can write this inequality. We can't combine these two into a three-part inequality. Three-part inequality always means and. But greater than is always going to be or. Any number to the right of positive 3 or to the left of negative 3. The solutions to inequalities will be intervals, as we see in these graphs. And we can either write those intervals using this algebraic form with these inequality statements, or we can use what's called interval notation. In interval notation, we give the left bound and the right bound for the corresponding interval. We separate those by a comma, and then we use round brackets like these if the endpoints are not included. That'll happen when there's no equals. And it's common to use the same type of brackets when you graph the interval on the number line. So here we're using these round brackets or open brackets because we're not including the endpoints. The interval notation for this solution set will contain two intervals that are unbounded. This one on the right goes to positive infinity. This one on the left goes to negative infinity. So the first interval here is negative infinity to negative 3, not including the negative 3. We always put the values from left to right. So this one has no lower bound. Negative infinity means this extends all the way to the left. We always use round or open brackets on infinity because we don't consider that a number you can actually include. The interval on the right is from 3 to positive infinity. So 3 is the lower bound, not included. And there is no upper bound. It goes all the way to infinity. This is the union symbol, which means or. So it means anything in this interval or in this interval. This shows us what any absolute value inequality with a less than will look like, and what any absolute value inequality with a greater than will look like. If you can remember this basic picture for the less than, and this one for the greater than, that'll help you set up the more complicated inequalities where we have an expression inside the absolute value and we have to solve for x. We'll look at an example of those in a second. Let's just finish this little introduction by looking at what happens if we have a less than or equal to, or a greater than or equal to. The only difference between the absolute value of x less than or equal to 3 and the absolute value of x less than 3 is that we're going to include the endpoints of this interval. Because now we want any number whose distance from 0 is either less than 3 units or equal to 3 units. So we get the same interval, but we use these square brackets, which are called closed brackets. That means we include the endpoints. For the algebraic inequality, we use the same thing we had here, except we have the or equals with each of these. And for the interval notation, we have the same interval we have here, except we use the closed or square brackets to indicate that the endpoints are included. So when we're setting up and solving inequalities with less than, we just have to pay attention to whether or not it has the equals, and that'll affect how we write the endpoints. For the absolute value of x greater than or equal to 3, we're going to get the same basic setup that we have here, except we're including the endpoints. So we'll use square or closed brackets in our graph. We'll put the or equals in our inequality statement, and we'll use the square or closed brackets on the endpoints of the interval notation. Here's the square brackets. Here's the or equals with our algebraic statement. And here's the square brackets on the interval notation. Remember, we never use square brackets on the infinity symbols. Those are not points that we can include. But we do use them on the endpoints here. One last note about the graph of these intervals on a number line. Most algebra books now will use brackets as we're using here, because they match the brackets we use in the interval notation. But sometimes you will see this with a closed circle when the endpoints are included, and an open circle when the endpoints are not included. So you might see this notation. And you could use either of these, with the open or closed circles, or with the brackets. So we can use these as templates when we solve absolute value equations and inequalities. We can use this model when we have absolute value equal to a positive number. We can use this model when we have absolute value less than a positive number. And we can use this when we have absolute value greater than a positive number. We already saw that when we have absolute value equal to a negative number, there are no solutions, because absolute values are never negative. We'll look at what happens when we get a negative number with these inequalities at the end of this video. First, we want to look at the case where we have an expression inside the absolute value and we have to solve for x. We've already seen that with equations. Here, we would set the expression inside the absolute value equal to the negative of this number or equal to the positive of this number, and then solve each of these two equations separately. Let's see how that works with the inequalities. In this example, we're asked to solve this inequality. We're going to give our answer in algebraic form, interval notation, and we'll graph the solution set on a number line. This is absolute value less than a positive number. This is already in standard form. Remember that we can't do anything else before this is written in standard form. Now remember the picture that we had for the absolute value less than a positive number. Absolute value less than positive 5 means we want whatever number we get on the inside of the absolute value to be less than 5 units from 0. So that gives us the interval from -5 to +5. Since this expression is not just the variable x, that's not going to be the final solution when we solve for x. That's saying that this expression, 2x minus 7, has to be between -5 and +5. Here we can use the three-part inequality. 2x minus 7 is greater than -5 and less than +5. So if you can remember this picture, for absolute value less than a positive number, this will tell you how to set up the two inequalities that we need to solve. And when we solve this, we really are solving two inequalities. So if we were solving the inequality here on the right, we would add 7 to both sides and then divide by 2. We would do the same thing when we solve the inequality on the left. We would add 7 to both sides and then divide by 2. So we can do that all at once. We can add 7 to all three parts of the three-part inequality and then divide by 2 on all three parts. And now we've isolated the variable. We have x is greater than 1 and x is less than 6. This is the algebraic form for the solutions of this inequality. It's easy to graph this on a number line. This is all the numbers that are greater than 1 and less than 6. Notice that this interval has the same form as the one we started with, but we have two new endpoints after solving for x. And this makes it easy to see what the interval notation will be. It's the interval with a lower bound of 1 and an upper bound of 6. So here are the three forms that we can use to give our solutions for these inequalities. In most cases, you'll be asked to give all three of these. My recommendation is to use this picture for the initial setup, then solve the inequalities, which will give you your algebraic form, then sketch the graph on the number line, because that makes it easy to see what the interval notation will look like. Notice in this case, we do not have an equals. This is strictly less than. So that means we use the strict inequalities here when we set up and solve. We do not put the or equals. And that means we use the open brackets for our graph and for our interval notation. If this had said less than or equal to, then we would use the square or closed brackets, and we would use or equal to on each of these inequalities. And of course, we would have the square brackets here in our final answer. But that's the only difference. The basic template is the same for any less than. And remember, when we solve an inequality or an equation, we're looking for the values of the variable that make this a true statement. And this is saying when the variable x takes a value between 1 and 6, then this expression 2x minus 7 will take a value between -5 and +5, and that makes this a true statement. So the solution set is the interval from 1 to 6, because those are the values of x that make this statement true. Now let's look at an example with a greater than. Here we have the same directions. Now we have a greater than, but notice this is not in standard form. So before we can do anything else, we need to write this in standard form. And we do that by isolating this absolute value. So let's subtract 5 from both sides. Now we have standard form, and since we have a positive value on the right, we can continue with the setup. Remember what the template looks like when we have the absolute value greater than a positive number. This says we're looking for values that have a distance greater than 4 units from 0. So we need this expression to have values that are either greater than +4 or less than -4, because these are all the numbers that are more than 4 units from 0. And again, this picture will tell us exactly how to set up the two inequalities that we need to solve. This expression inside the absolute value must be less than negative 4 or greater than positive 4. So the picture tells you everything you need to set up the two inequalities. Now we'll solve for x in each of these inequalities. First, we subtract 1 from both sides to isolate the variable term, and now we divide both sides by the coefficient of 3. And that gives us the algebraic form for our answer. X is less than negative 5/3, or x is greater than 1. Let's go ahead and sketch this on the number line. It'll look just like the graph that we started with, except now we have two new endpoints after we solve for x. When one of your endpoints is a fraction or decimal, you can approximate that point on the number line. Negative 5/3 is equal to negative 1 2/3. So you can just place this point somewhere between negative 1 and negative 2 on the number line. And now, using this graph, it'll be easy to write the interval notation. This interval here on the left is going from negative infinity to negative 5/3, and the interval on the right is going from 1 to positive infinity. And remember, we use a union here because any number in this left interval or in this right interval will be a solution to this inequality. This gives us a template that we can use for every greater than. And if this is greater than or equal to, the only difference is these endpoints will be included. So we would use the or equals to with each of these inequalities, and we'll use the square brackets on the endpoints. But remember, we never use the square brackets on infinity. We always use the open or round brackets for infinity. Let's end by looking at what happens if we have a negative number with one of these inequalities. So here, let's consider the cases absolute value less than a negative number and absolute value greater than a negative number. We've already seen the case absolute value equal to a negative number, and we know that this has no solutions. That's because the absolute value is always positive or 0. So it can never equal a negative number. If the absolute value were less than a negative number, then the absolute value would also have to be negative, which is impossible. So absolute value less than a negative number also has no solutions. Now let's consider the case absolute value greater than a negative number. The absolute value is either positive or it can equal 0 if you have a 0 on the inside. In either case, a positive number or 0 will always be greater than a negative number. So any number inside this absolute value will make this a true statement. And that means that all values of x are solutions. So we say the solutions are all real numbers. The graph of this would be the entire number line, and the interval notation would be the interval from negative infinity to positive infinity. It's not difficult to remember these if you understand that this statement is always true and these statements are always false. Because a positive number or 0 is always greater than a negative number, and a positive number or 0 is never less than a negative number or equal to a negative number. It won't matter what negative number, and it won't matter if these are strict inequalities, or if this is greater than or equal to, or less than or equal to. It also won't matter if we have a more complicated expression inside the absolute value. It is important that these are in standard form. For example, here we have an absolute value with a less than negative 2, but this is not in standard form. And this is not saying that the absolute value is less than negative 2. It's saying that the absolute value minus 9 is less than negative 2. So our first step is always to rewrite this in standard form. In standard form, we do not have that the absolute value is less than a negative number. So in this case, we would be able to set up our two inequalities and solve. using the template that we use for all absolute value less than a positive number. Here we have an absolute value with a greater than and a positive number on the right. But again, this is not in standard form. And this is not saying that the absolute value is greater than or equal to positive 2. It's saying the absolute value plus 5 is greater than or equal to positive 2. So we would first need to write this in standard form. And now we have absolute value greater than or equal to a negative number. So here we have a statement that's always true, just like the case above. So the solutions will be all real numbers. No matter what we plug in for x, we will always get a true statement.